Our next topic is similar figures. We'll also be doing some construction, so make sure you've got that compass and protractor ready. So figures that are the same shape but not necessarily the same size are similar. These two fellows are similar, and these two aren't. Now the ones on the left are similar because the larger guy is twice as wide and twice as tall as the shorter guy. The ones on the right are not similar because even though the larger guy is twice as tall, he's about 4 times as wide. Now we'll be talking a lot about triangles, although the things that we're going to talk about in terms of similarity apply to other shapes as well. So two triangles are similar if their corresponding angles are congruent. These two triangles are similar. Now it's not obvious from looking at them that they are because we really don't know anything about the two triangles. So in the smaller triangle we have a 35-degree angle, and we also have a 35-degree angle in the larger triangle. Those two angles would be considered corresponding. We have an 80-degree angle in both triangles. Those are corresponding angles. And we have a 65-degree angle in both triangles, so those are corresponding angles. Now, if we label the vertices of the triangles, we'll be able to give them names. And we can also write a similarity statement which says that not only the two triangles are similar, but it also states which parts are congruent. So the triangle on the left we can call triangle ABC. The symbol we use for similar is kind of a squiggle, kind of a tilde. And we would say that triangle ABC is similar to triangle FED. Now the order of those letters is important because the order is explaining which angles are congruent. So angle A, which is the first angle mentioned in the name of the smaller triangle, is congruent to angle F, which is the first angle mentioned in the name of the larger triangle. And angle B, which is the second angle mentioned in the name of the smaller triangle, is congruent to angle E because it's the second mentioned in the name of the larger triangle. So be very careful when you are writing statements about the similarity of two triangles, because the order that you write the names of the vertices in is implying which angles are congruent. Now if we do have two triangles that are similar, then their corresponding sides are in proportion. So let's say we have these two triangles, triangle ABC and triangle FED, and they are similar. If we look at the sides that are opposite the angles that are congruent, for example, side BC is opposite angle A, and side ED is opposite angle F. Those two sides would be considered corresponding. They are opposite angles that are congruent. So suppose I know that side BC measures 6 units and side ED measures 12 units. So I've just established a relationship between the corresponding sides. And with that, I can look for relationships between other corresponding sides. For example, in the smaller triangle, side AB measures 7 units and it's opposite angle C. So which angle in the larger triangle corresponds to angle C? Well, that's angle D. So that means the side opposite angle D has to correspond to the side that measures 7 units in the smaller triangle. Now we don't know how long that is, but we can find its length because we know that the corresponding sides of these two triangles are in proportion. So we could say that the side that measures 12 in the larger triangle corresponds to the side that measures 6 in the smaller triangle, and the side that measures x in the larger triangle corresponds to the side that measures 7 in the smaller triangle. So we can solve that proportion to find the length of x, which is 14 units. Now there's something else you might have noticed here, and that is that there's a relationship that we can see between these corresponding sides. So for example, if we look at the smaller triangle and the larger triangle, and those corresponding sides that measure 6 and 12, you might have noticed that the 12 is twice as big as 6. And in fact, the 14 we just found is twice as big as the 7 that's the length of its corresponding side. Well, that multiplier is called a scale factor. And we could say in this case, the scale factor from the smaller to the larger triangle is 2, which simply means we double the lengths of the sides of the smaller triangle to get the sides of the larger triangle. You might also have noticed that scale factor showing up in the proportion. We compared the lengths of the larger triangle to the smaller triangle in each of our ratios. So when you look at the 12 to 6, you'll see 12 divided by 6 is 2, and the x to 7, well, 14 divided by 7 is also 2. Now how about this picture? There's two triangles in it. Are the two triangles similar in the picture? We don't know the lengths of any of the sides, so we can't tell if the corresponding sides are proportional. And we weren't given all the angle measures, so we can't say that we have pairs of corresponding angles that are congruent. So how can we tell that we have similar triangles here? Well, let's see what we do know. We know that angle A and angle E have to be congruent, and that's because it was given in the picture. They're both right angles. Now we could also say that angle ACB in the larger triangle is congruent to angle ECD in the smaller triangle. Think about why that's true. It's something we've talked about already. There's a relationship between those two angles because the angles are formed by these intersecting segments. And those two angles are called vertical angles, and we know that vertical angles are always congruent. Now that leaves us with one more angle in each triangle. We've stated that these vertical angles are congruent, and you'll notice how we can mark congruent angles in our picture. So we have two more angles that are left, angle B and angle D. Are those two congruent? Well, they're also congruent because we know that all the angles in a triangle have to add up to 180 degrees. And we've already established that we have two pairs of congruent angles in both of these triangles. So that means the remaining angles, angle B and angle D, would have to be congruent. So now that we've got three pairs of congruent angles in our two triangles, we know that we have similar triangles. And if we want to write a similarity statement for these two triangles, we'll just be careful about the order that we write the vertices of the triangles to make sure that we've matched up the congruent angles. So we could say that triangle ACB is similar to triangle ECD. So let's try a real-world problem that involves similar triangles. Allie is 4 feet tall and her shadow is 6 feet long. A nearby flagpole has a 36-foot-long shadow. How tall is the flagpole? Well, let's draw a picture of what's going on. Here's the sun, here's Allie, she's 4 feet tall, and there's her shadow that's 6 feet long. The flagpole has a shadow that's 36 feet long, but we have no idea how tall the flagpole is. Now what's important to know is that the sun is the same sun for both Allie and the flagpole, so the angles created by the sun are exactly the same. So if we think about these triangles that are formed by each of the vertical things, meaning Allie and the flagpole, and the ground, what we've got is two similar triangles. In fact, two similar right triangles. So, since we have similar triangles, we can say that the corresponding sides have to be proportional, which means the x is corresponding to the 4, and the 36 is corresponding to the 6. So we can solve that proportion and find out that x, the height of the flagpole, would have to be 24 feet tall. Now there's one other interesting thing that goes on with similar figures, and that has to do with area. So if two triangles are similar, then the scale factor of their areas is the square of the scale factor of their side lengths. Now this says triangles, but it actually works for any figures that are similar to each other, whether they're squares or they're pentagons or they're just blobs that are similar to each other. In this case we have triangles, and we know how to find the area of a triangle. So if we wanted to find the area of this small triangle, since we've got two sides that are perpendicular to each other, we can call them the base and the height. So the area of the small triangle is 1/2 times 6 times 4, which is 12 square units. Now obviously if we know the lengths of the sides of the larger triangle, we could find its area using that same area formula. But let's do this a little differently. If we can find the scale factor between the two triangles, we can use that to find the area of the larger triangle. So let's look at corresponding sides of these two triangles to find the scale factor. So to go from the small triangle, which has a side of 6, to its corresponding side in the large triangle, which is 36, we can see that we have a scale factor of 6 that relates the lengths of the sides. Now for the areas, we can say that the area of the large triangle is that same 6 squared times the area of the small triangle. So in this case, that would be 36, that's the square of the scale factor of the sides, times the 12, which is the area of the small triangle. So the area of the large triangle has to be 432 square units. So we've got two constructions we're going to look at. First, we're going to learn how to copy an angle, and then we're going to see how we can use that construction to construct similar triangles. Okay, so what we're going to do is construct a copy of this angle. Now remember, the only place you're going to be allowed to put the point of your compass is on points in your construction. So keep that in mind as we're doing this. So the first thing we're going to do is over here, I'm just going to put an array that I'm going to copy this angle to. So I'll just maybe do something like this. And I'll say that that ray is going to be part of my copied angle. And that ray has a point right there. So let's keep that in mind. Now this angle that we've started with has only one point, which is right here. I'm allowed to put the point of my compass on that point. So what I'm going to do is put the point of my compass there and make an arc that goes through both rays of this angle that I want to copy. Then I'm going to, without moving the measurement on my compass, come over here to the ray that I'm copying that angle to, and I'm going to make the same kind of arc like that. Alright, so now I'll come back over here to my original angle, and I've created 2 points, 2 intersections right here and here, where this arc that I drew is intersecting these 2 rays. So what I'd like to do is measure that distance. So I will measure it just like that. That's how far it is. And I want to measure that same distance over here on my new copied angle. So without changing this distance on my compass, it's still this same distance. I'm going to put the point of the compass on this new intersection and make an arc through that first arc that I drew. Now that gives me another intersection, which basically creates another point. And if I connect that point with the end point of the ray, what I will have is an angle that's congruent to the one that I started with, but I've constructed that copied angle. So now we're going to use that idea of constructing a copy of an angle to construct a triangle that's similar to another triangle. Okay, let's say I want to construct a triangle that's similar to this one, but has sides that are twice as long. So the first thing I'm going to do is construct a side of my larger triangle and make it twice as long. Now remember, I may have all these lovely symbols on my protractor that seem like they ought to let me measure something, but you cannot measure with those symbols. So let's say that this is one vertex of my larger triangle, and I want my larger triangle to have a side that's twice as long as this. So I'm going to come over here and measure out 1, I may have to extend this a little bit, 2, so 2 lengths of that smaller triangle's side length. Now once I've got those 2 lengths, I can put an endpoint right here. So I know that this line segment is twice as long as this line segment. Now what I need to do next is copy those angles. So I'm going to put the point of the compass on this vertex and make an arc. And then I think I'm just not going to change the size of the compass. I'm going to leave it the same. Put it on this vertex and make an arc. Now I'll come over here to the segment that represents the side of my larger triangle. I have not changed the compass, but I'm going to do those same 2 arcs, if I can do this without it slipping. So there's 1 and 2. Now I need to go back over here to the original triangle and I need to do some measuring. So from this vertex, this one that's on the left, I'm going to measure the distance between these 2 intersection points. So it's that far. I need that same distance over here. So I'll put the point of the compass on this intersection and make an arc. And if I extend this line segment, I'm going to go through that endpoint and this intersection. I know that the side of my triangle has to be along that line segment. Now I'll come back over here to this arc and I will measure its size. It's about that long. And I want that same distance from here to here. So I'll make an arc. That is a bad looking arc. Let me try again. All right, and where those intersect, if I connect that up with this endpoint and extend it, then where these 2 intersect is the 3rd vertex of my similar triangle. As usual, we'll get a chance to practice this in class.